Hello everyone, myself Harsh Kumar, student of BSc Chemistry Honours second year. This is my video for visually impaired students on topic alcohols. Introduction. Alcohols constitute a class of compounds which are regarded as hydroxy derivatives of hydrocarbons. They are further classified as mono, di, and trihydric alcohols according to the number of hydroxyl groups present in their molecules is 1, 2, or 3 respectively. Alcohols containing 4 or more hydroxyl group are known as polyhydric alcohols. Thus, we have methyl alcohol as monohydric, glycol as dihydric, glycerol as trihydric, sorbitol as polyhydric. It may be pointed out that dry, tri, and polyhydric alcohols always have the OH group attached to different carbon atoms. This is because a compound having more than one OH group linked to the same carbon atom is unstable and at once eliminates the elements of water as shown below. Aromatic hydroxy compounds fall off in two categories. These are first, aromatic alcohols. These compounds are in which the hydroxyl group is present on the side chain. These may be regarded as alcohol in which OH group is attached to an aryl substituted alkyl radical. An important example of such a compound is benzyl chloride. Phenols, these are compounds which contains hydroxyl group or groups directly attached to an aromatic ring. For example, phenol is an important example. The properties of phenol are markedly different from the properties of alcohol, and chemistry is discussed separately in chapter 2. Monohydric alcohols. These are alcohols having the general formula ROH, where R may be simple or substituted alkyl group. Thus, we have methyl alcohol, ethyl alcohol, benzyl alcohol. Saturated monohydric alcohols are also known as alcohols, as these are derived from alkenes by the replacement of a hydrogen atom by a hydroxyl group. Alcohols can be represented by general formula CnH2n plus 1 OH, where N is the number of carbon atoms. Classification. Monohydric alcohols may be further classified as primary, secondary, or tertiary alcohols as given below. First, primary alcohol or 1-degree alcohols. These are alcohols in which the hydroxy group is attached to primary carbon atom. For example, ethyl alcohol, N-propyl alcohol, benzyl alcohol. It is apparent that the carbon which carries the OH group has at least 2 hydrogen attached to it. In other words, primary alcohol have the characteristic group CH2OH present in them. Second, secondary alcohol or 2-degree alcohols. These alcohols contain the hydroxy group attached to a secondary carbon atom. For example, isopropyl alcohol, secondary butyl alcohol. In these alcohols, the carbon carrying the OH group has only one hydrogen atom attached to it. As such, the group characteristic in these alcohol is CHOH. Third, tertiary alcohol or 3-degree alcohols. These are alcohols in which the hydroxy group is attached to a tertiary carbon atom. For example, tert-butyl alcohol. It is clear that the carbon carrying the OH group has no hydrogen attached to it. This means that the characteristic group present in these alcohols is COH. Nomenclature of monohydric alcohols. Monohydric alcohols are named by 3 different systems. First, the common system. According to this system, which is used only for the simpler alcohols, alcohols are named by adding the word alcohol to the name of alkyl group present in the molecule. For example, methyl alcohol, ethyl alcohol, N-propyl alcohol, isopropyl alcohol, tert-butyl alcohol, and benzyl alcohol. Second system is the carbonyl system. According to this system, methyl alcohol is called carbonyl and other alcohols are named as alkyl derivatives of carbonyl. For example, carbonyl, methyl carbonyl, dimethyl carbonyl, and trimethylcarbinol. However, this system is used only rarely. The IUPAC system. In this system, alcohols are named in accordance with the general IUPAC rules. The main points involved in the nomenclature are summed up below. First, the longest carbon chain containing the carbon atom carrying the hydroxy group is selected as corresponding to the parent hydrocarbon. The alcohol is named as derivative of this hydrocarbon by replacing the final E of the name of hydrocarbon by the suffix ol. The parent chain of carbon atom is numbered from that end, which gives the lowest possible number to the carbon carrying the hydroxyl group. The name of alcohol is then written as one word by writing the names of the side chains or substituent along with the position in alphabetically order, followed by the name of the parent alcohol. For example, ethanol, butanol, 2-methylpropane 1-ol, 2-methylpropane 2-ol, etc. Structural isomerism. Monohydric alcohols exhibit three types of structural isomerism. First, chain isomerism. This type of isomerism is due to the difference in the nature of carbon chain attached to hydroxyl group. It is exhibited by alcohols having 4 or more carbon atoms. For example, butane 1-ol, 2-methylpropane 1-ol. Second is position isomerism. It is due to the difference in the position of hydroxyl group in the chain of carbon atoms. For example, butane 1-ol, butane 2-ol. Third is functional isomerism. Monohydric alcohols also exhibit functional isomerism with another class of oxygen derivatives, namely ethers. For example, ethanol, methoxymethane. Method of formation. First, reduction of carbonyl compound. Alcohols can be easily obtained by the reduction of aldehydes, ketones, carboxylic acid, esters, etc. by a variety of reducing agents as discussed below. First, reduction of aldehyde and ketones. Aldehydes can be reduced to primary alcohols and ketones to secondary alcohols in a number of ways as given below. A. Catalytic hydrogenation. Aldehydes and ketones can easily be reduced to primary and secondary alcohols respectively by hydrogenation in the presence of catalysts such as nickel, palladium or platinum, that is given below. Catalytic hydrogenation of an aldehyde or ketone containing other easily reducible groups such as carbon-carbon double bond will furnish product in which both the functional group are reduced. Therefore, this method cannot be used if it is desired to carry out the selective reduction of only carbonyl group, keeping the other group intact. Second, reduction with complex metal hydrides. The reduction of aldehyde and ketones to prepare alcohol is usually carried out in the laboratory with complex metal hydrides such as lithium aluminum hydride LiAlH4 and sodium boron hydride NaBH4. Sodium borohydride is easier to handle and can be used either in water or alcohol solution. The reduction product initially formed gets hydrolyzed to form alcohol. Lithium aluminum hydride reacts violently with water and alcohol. It can be used only in the aperiodic solvents such as dry ether or tetrahydrophone. The product initially formed is then subjected to hydrolysis to get the alcohol. Mechanism. Reduction of aldehyde and ketones by both LiAlH4 and NaBH4 occurs through the nucleophilic attack of the hydride ion on the carboxyl group to form a compound containing an OB or OAl bond. This species has still got 3 metals hydrogen compound and react further with the 3 more molecules of carbonyl compound. The metal alkoxide intermediate thus formed is hydrolyzed to get the alcohol as shown below. It may be seen that 1 mole of NaBH4 or LiAlH4 reduces 4 moles of aldehyde or ketone. Both LiAlH4 and NaBH4 are selective in their reducing action. In the reduction of aldehyde and ketones containing isolated carbon-carbon double bonds, only the carbonyl group gets reduced by these reagents. In the case of compounds which contain carbon-carbon double bond in conjugation with carbonyl group, sometimes double bond may get reduced along with the carbonyl group. The chances of reduction of both functional group are more with the LiAlH4 than with NaBH4. It may be recalled that a reagent which attacks only one functional group and not the other functional group is also present is known as regroselective reagent. Third is reduction of esters. Reduction of esters constitutes of convenient method of preparation of alcohols. The reduction is generally carried out by the following methods. First, blank reduction. This method involves reduction of esters to alcohols by the treatment with sodium in alcohol. The reaction leads to the formation of a mixture of two alcohols, which is formed from a alkoxy group ROH, and the second which is formed from the alkyl group. Mechanism. The reaction is believed to take place in a number of steps and involves the transfer of one electron at a time from sodium metal as summed up ahead. Second, reduction with LiAlH4. Esters can be reduced with LiAlH4 to yield a mixture of two alcohols, as in case of blank reduction. Mechanism. The reaction takes place by the addition of hydride ion to the carbonyl part of ester group. This is followed by elimination of alkoxide ion to yield an aldehyde intermediate which is not isolated. Further reaction of LiAlH4 with aldehyde group gives primary alcohol. Catalytic hydrogenation. On an industrial scale, alcohols are obtained from esters by catalytic hydrogenation in the presence of copper chromyl catalyst. Fourth, hydration of alkenes. Alkenes can be hydrated from alcohol to form alcohols either through addition by sulfuric acid or by direct hydration as described below. Fifth is oxymercuration demercuration of alkenes. It is a very convenient two-step method for preparing alcohols from alkenes. When treated with mercuric acetate in a water tetrahydrofuran solution, alkenes form organometallic compounds. These mercury compounds are reduced by sodium borohydride NaBH4 to yield alcohols, that is given below. In the first case, water and mercury acetate add to the double bond. This is known as oxymercuration. In the second step, the sodium borohydride reduces the mercurial compound and the mercury acetate group gets replaced by hydrogen. This is known as demercuration. Both the steps take place very rapidly and conveniently at room temperature. The organomercurial compounds formed in the first step is not isolated but is reduced in situ by sodium borohydride to form alcohol in high yield, more than 90%. Oxymercuration demercuration is highly regroselective and the alcohol formed is in accordance with Markovnik's of addition of water to the carbon-carbon double bond. 6. Hydroboration oxidation of alkenes. When treated with diboron BH3 twice, alkenes undergo hydroboration to form alkyl boranes. The alkyl boranes are readily oxidized by the hydrogen peroxide in alkaline solution to form alcohols. Thus, the net result of this reaction also is the addition of water to the alkenes to form alcohols. Hydrogenation oxidation is also a regroselective reaction, and the alcohol obtained is such as anti-Markovnikov addition of water to alkenes has taken place. Such as this method can be used for the preparation of alcohols which cannot be prepared by other methods of hydration of alkenes. For example, it may be noted that due to anti-Markovnikov addition, only primary and secondary alcohols can be prepared by this method. 7. Grignard synthesis. By the far most important method for the preparation of primary, secondary, and tertiary alcohols is by the reaction between a Grignard reagent and a carbonyl compound such as an aldehyde or a ketone. The addition product initially formed is decomposed with water, preferably in the presence of acids such as HCl or H2SO4 to get the alcohols. The general reaction may be depicted as follows. If the carbonyl compound used in the above reaction is formaldehyde, the final product is a primary alcohol. When the carbonyl compound used is some aldehyde other than formaldehyde, the final product is a secondary alcohol. Use of a ketone to react with Grignard reagent leads to the ultimate formation of tertiary alcohols. 8th, by the hydrolysis of alkyl halides. The hydrolysis of alkyl halides with aqueous solution of sodium or potassium hydroxide or moist silver oxide results in the formation of alcohol. By the hydrolysis of ester, the hydrolysis of ester with alkyl solution is generally employed for the preparation of alcohols from naturally occurring esters. 10th, by the fermentation of carbohydrates. This method has been used since very early time for the large-scale preparation of ethyl alcohol. The carbohydrate employed in this process is either sugar or some starchy material like potatoes, barley, rice, or maize. Physical properties of alcohol. Due to presence of OH group in their molecules, alcohols are polar compound. Oxygen is more electronegative than either carbon or hydrogen, so that the electrons of CO bond as well as OH bonds are displaced towards the oxygen atom. Therefore, the oxygen atom carries partial negative charge, while both carbon and hydrogen attached to the oxygen carry partial positive charges. Moreover, like water, alcohol molecules also has a bent structure, so that we may represent alcohol molecule as follow. Because of their bent structure and polar nature of CO and OH bonds, alcohol possess considerable dipole moment. The above structural features of alcohol have a strong influence on the physical and chemical properties of alcohol as discussed below. First, physical state. The lower alcohols are colorless liquids having a distinct alcoholic smell and a burning taste. The higher members are colorless, tasteless, waxy solids. Second, associated state. Hydrogen bonding. Since molecules containing a hydrogen attached to strongly electronegative oxygen, extensive intermolecular hydrogen bonding exists between alcohol molecules. As a result, alcohol exists in the form of associated molecules and not simple monomeric molecules. Third, boiling points. The boiling points of alcohols are much higher than those of hydrocarbons or ethers of comparable molecular weight, as is evident from the given examples. The high boiling points of alcohols can be explained in the terms of extensive intermolecular hydrogen bonding in alcohols. Large amount of energy is required to break these hydrogen bonds which hold the alcohol molecules together in the associated state. Therefore, alcohols boil at much higher temperature than alkenes, ethers, etc., which do not form intermolecular hydrogen bonds. Amongst themselves, the boiling points of isomeric alcohols are in the order primary, then secondary, then tertiary. This is because out of isomeric alcohols, primary alcohols are the most polar and form hydrogen bonds to the maximum extent as compared to the secondary and tertiary alcohols. With the increase in the molecular weight, the boiling point increases regularly. Solubility. The lower alcohols are highly soluble in water, but the solubility decreases with the increase in the molecular weights. The high solubility of lower alcohols is due to the formation of hydrogen bonds between alcohol and water molecules. Chemical properties. The hydroxyl group present in the alcohol is a very reactive group, and the characteristic reactions of alcohols are the reactions of OH group. In general, the reactions of alcohols may be divided into the following three categories. First, reaction involving the cleavage of OH bond, that is ROH. Second, reactions involving the cleavage of COH bond, that is ROH. Third, reactions involving both alkyl and hydroxyl group of the alcohol molecules. First, reactions involving the cleavage of OH bond. In general, order of reactivity of alcohol in the type of reaction is primary alcohol, then secondary alcohol, then tertiary alcohol. Explanation. The cleavage of OH bond oxygen, which is the more electronegative than a hydrogen, takes away both the electrons of the shared electron pair. Therefore, relative reactivities of alcohol in these reactions can be explained in the terms of hydrogen releasing plus I inductive effect of the alkyl group. As we move from the primary to secondary to tertiary alcohol, the number of alkyl groups attached to the carbon carrying the OH group increases from 1 to 3. Due to this, the electron density and around oxygen goes on increasing on moving from primary to secondary to tertiary alcohols. The result is that the electron of the OH bond cannot be sufficiently drawn towards oxygen, and the age of cleavage of OH bond decreases. Thus, the order of reactivity in the reaction involving the cleavage of OH bond is primary, then secondary, then tertiary. Reaction with acid halide or acid anhydride. When alcohols are heated with an acid halide or acid anhydride, the hydrogen of OH group is replaced by allyl group RCO, and once again an ester is formed. The reaction is known as acylation. Takes place more rapidly than esterification with carboxylic acid themselves. Thus we have. It may be noted that in case of polyhydric alcohol, hydrogen of each OH group is replaced by acyl group to form polyesters. For example, 1 mole of glycerol reacts with 3 moles of CS3COCl to form an triester. Reactions involving cleavage of COH bonds. In these reactions, the bond between the carbon of alkyl group and oxygen of the hydroxyl group get ruptured. The order of reactivities of alcohols in this type of reaction is tertiary, then secondary, then primary. Explanation. The above order of reactivity can also be explained in the terms of plus I inductive effect of alkyl groups. As we move from primary to secondary to tertiary alcohols, the number of alkyl groups attached to carbon carrying the OH group increases. Due to this, the electron of the CO bond are pushed more and more towards oxygen. As a result, CO bond becomes more and more polar and therefore more reactive. In other words, tertiary alcohol would be most reactive in such reactions, and the reactivity will be lesser and still lesser in case of secondary and tertiary alcohols. Reactions involving both alkyl and hydroxyl groups. Acid dehydration. When alcohols are heated with sulfuric acid, phosphoric acid, or boric acid, or when their vapors are passed over heated aluminum oxide, alcohols get dehydrated to form alkenes. The reaction between alcohols and sulfuric acid is very sensitive to conditions of reaction, furnishing different products under different conditions. Mechanism of dehydration. The mechanism of dehydration of alcohol involves the formation of a carbocation as an intermediate. The reaction is believed to take place in 3 steps. In the first step, alcohol combines with a hydrogen ion to form protonated alcohol or oxonium ion. The second step involves the dissociation of oxonium ion and formation of carbocation. Finally, the carbocation loses a hydrogen ion to yield alkene. The various steps are illustrated ahead with the help of ethyl alcohol. Orientation of dehydration. Many alcohols give rise to mixtures of isomeric alkenes. Dehydration. The ratio of alkenes formed in the particular reaction depends upon the reaction conditions. However, in general, it may be stated that dehydration of an alcohol favors the formation of more stable alkene. Second, oxidation. Oxidation of alcohol can be carried out with a variety of reagents such as aqueous, acidified or alkaline potassium permanganate, acidified sodium or potassium dichromate, dilute nitric acid or CrO3 in pyridine. The age of oxidation and the nature of the product obtained depends on the type of alcohol employed. First, primary alcohols. Primary alcohols are easily oxidized to aldehydes and then to acid containing the number of carbon atoms as the original alcohols. It is possible to arrest the reaction at the aldehyde stage by using a suitable oxidizing agent such as acidified K2Cr2O7 and distilling away the aldehyde as soon as it is formed. Second, secondary alcohols. On oxidation gives first ketone with the same number of carbon atoms. Ketones are further oxidized only on drastic treatment to give acid containing lesser number of carbon atoms. Tertiary alcohols fail to undergo oxidation in neutral or alkaline solution. However, acid oxidizing agents they are in presence with acid oxidizing agents they are oxidized to give ketones and acid containing lesser number of carbon atoms than the original alcohols. Action of hot reduced copper. Different classes of alcohol furnish different products with their vapors when their vapors are passed over reduced copper at high temperature 475 to 575 Kelvin. Distinction between primary, secondary and tertiary alcohols. Lucas test. The most convenient and commonly used method for distinguishing between different classes of alcohols is Lucas test. It consists in treating the alcohols with Lucas reagent, which is an equimolar mixture of concentrated hydrochloric acid and anhydrous zinc chloride. Appearance of cloudiness in the reaction mixture indicates the conversion of alcohol into alkyl chloride. It has been observed that a tertiary alcohol reacts immediately and therefore cloudiness appears immediately. A secondary alcohols react within about 5 minutes when the cloudiness appears. A primary alcohol does not react appreciably at room temperature and therefore no cloudiness appears. Interconversions of primary, secondary and tertiary alcohols. It is possible to convert one class of alcohol into another class as illustrated below. Conversion of a primary alcohol into secondary alcohol. N-propyl alcohol into isopropyl alcohol as given below. Dihydric alcohols. Dihydric alcohols are compounds containing two hydroxyl group attached to different carbon atoms in their molecules. They are known as diols in IUPAC system and glycols in common system. For example, ethylene diol, ethylene glycol. Nomenclature. First common name. The two hydroxy group in a glycol are usually attached either to adjacent carbon atoms called 1,2 or vicinal glycols or carbon atoms situated at the extreme ends of the carbon chain called polymethylene glycols. In the common system, vicinal glycols are named after the common name of corresponding alkene, while polymethyl methylene glycols are named according to the number of methylene groups present in the molecule as given below. IUPAC names. In the IUPAC system, all dihydric alcohols are named as diols of parent alkenes. The positions of OH group being indicated by suitable numbers as given below. The longest straight chain of carbon atoms, which must include the two carbons carrying the COOH groups, is selected and the name of the corresponding hydrocarbon is written. The chain is numbered from the end, which gives the lowest possible number to the carbon carrying OH, the first OH group. The suffix diol is added to the name of parent hydrocarbon along with the position of OH groups. The name of the side chain and the other substituent, if any, are prefixed before the name of the compound along with their position in alphabetical order. Physical properties. Physical state. Glycols are generally colorless, viscous liquids having a sweet taste, high melting and boiling point. Glycols undergo intermolecular hydrogen bonding to a greater extent than monohydric alcohols. This is because they contain two sites for hydrogen bonding per molecule. As a result of extensive hydrogen bonding, glycols have much higher melting and boiling point as compared to monohydric alcohols. Solubility. Glycols have greater solubility in water than the monohydric alcohols. Chemical reactions. Like the monohydric alcohols, glycols exhibit the usual reactions of hydroxyl group, such as reaction with a metal like sodium, reaction with halogen, acid, esterification, etc. At the same time, glycols undergo certain reactions that are typically only of alcohols having two or more alcoholic groups. Reaction with organic acid. Glycols react with the organic acid to form mono or diester depending upon the relative amount of glycol and acid. Oxidation. Glycols give different products on oxidation under different conditions. In general, the oxidation may be depicted as follows by the considering the example of ethylene glycol. Oxidative cleavage of 1,2-glycols. When treated with periodic acid HiO4 or lead tetraacetate PbOOCCH3 4, the compounds contains two or more OH group attached only to the adjacent carbon atoms. Undergoes oxidative cleavage. The reaction breaks carbon-carbon bonds and yields carbonyl compound, aldehyde, ketones, etc. as oxidation product, that is given below. The oxidative cleavage of 1,2-glycols with the periodic acid, also known as Malaprade reaction. Utility of the reaction. The reaction usually takes place in the quantitative yield and is very useful in the structure determination, particularly in the study of carbohydrates. It gives valuable information by determining the quality of oxidizing agent used and the nature and amount of products formed as illustrated below. To determine whether the OH groups are present in vicinal position or not. Qualitatively, the occurrence of reaction between polyhydric alcohols and HiO4 is established by the formation of a white precipitate of AgIO3 on adding AgNO3 solution to the reaction mixture. If the PPT is formed, it means that the given polyhydric alcohol reacts with the HiO4. Therefore, it must have OH groups attached to the adjacent carbons. On the other hand, if no PPT is formed, it means that a given alcohol does not react with the HiO4 and the OH groups are not attached to the adjacent carbons. Mechanism. Oxidation with periodic acid. Oxidative cleavage with the periodic acid is believed to take place through a cyclic intermediate formed by the attack of periodate ion IO4 negative on a glycol as shown below. Important observations. Relative stability of carbocation. In case of glycols having different groups attached to the 2-hydroxyl group, the OH group which get eliminated is one which would produce a more stable carbocation. Second, migratory aptitude of groups. In the case of glycols having a different groups attached to the 2-hydroxyl group, it is not quite easy to predict the migratory aptitude of the group. In general, phenyl group migrates in preference to alkyl group, and hydrogen migrates in preference to both these groups. Stereochemistry. It may be emphasized that the migrating groups, that is methyl group in the given example under mechanism, is not completely detached from the carbon. It is living till it have attached itself to the electron deficient carbon as shown below. This would naturally mean that the migrating group in pinnacle rearrangement will retain its configuration. That is, the new bond found will have the same relative position as the held previously by the old bonds. If the migrating group were to get completely detached before attaching itself to the electron deficient carbon, it would lead to the racemization in case of chiral structures, but actually no racemization takes place. Thank you.